We've been sort of talking about solutions here, and we finished up the previous chapter. We talked about solids and some calculations involving unit cells and how solids sort of come together, and how to calculate sort of density and properties like that of solids. We've now sort of transitioned into solutions. We're going to talk a little bit about, again, some of the solubility aspect of solutions, why, again, some of them do mix together, some don't. We'll review a little bit of the concentrations as we talked about. And as we talked about last time, we'll kind of finish up this chapter when we get there, talking about other properties of solutions, which are referred to as colligative properties. And those are guys that, again, sort of deal with um, things like boiling points, freezing points, and things that affect those sort of temperatures. So we got into solutions and sort of talking about the idea of solubility, and this idea that when we talk about sort of solubility, a very common phrase usually comes up, and that's the idea of like dissolves like. And basically, what that means, and really, as we sort of touched upon yesterday, really what allows sort of solutions to interact with each other, or really anything to sort of interact with each other, is really those intermolecular forces that we spoke about in the previous chapter. And when things come to interact with, say another molecule, another substance, another solution, whatever it may be, they're looking to really interact with them the way that they interact with themselves. So, if they sort of use like dipole dipole interaction with themselves, when they come in contact with, say, another substance, they also are looking to use that similar type of intermolecular force. And what we see is that things that share very similar sort of intermolecular forces as sort of their main intermolecular force that they use, are able to really sort of be soluble in each other. They're able to mix with one another because they really have a way to interact with one another, is really where it comes down to. They have a way to sort of interact with some other substance, for example, the same way that they would interact with really themselves. When we get a couple of things that really are trying to use sort of different intermolecular forces, they really don't have a way to long term maintain some type of interaction. So when we talk about like dissolves like, what we're talking about again are things that share similar intermolecular forces and also share sort of similarities. So typically things that are soluble in each other will kind of be similar type of properties or molecules, like polar and polar things are soluble in each other. Again, they both would use some type of dipole dipole interaction. They may use hydrogen bonding interaction, but again, they would be using the same type of intermolecular force. Same thing with something that's ionic and something that's polar. Again, here they both essentially can use really dipole dipole interaction, ion dipole interaction. Things that are nonpolar and nonpolar are also going to be soluble in each other. Now, that's because they both can use really the nonpolar intermolecular force, which is dispersion forces. So they both can use dispersion forces. That's how they normally interact. That's how they normally behave. So they are going to be just fine when they sort of come in contact with each other. It's really, again, as we talked about, you get into a little bit of trouble in terms of solubility when we kind of cross over and try to take something that's polar and something that's nonpolar. Again, here, this guy is going to try to use probably some type of dipole dipole interaction, perhaps, again, or hydrogen bonding or something of that nature. And this guy, for the most part, are just going to use dispersion forces. So, over the long period of time, these two guys really don't have a pretty fixed way that they can maintain some type of interaction with each other. And that's why those things are typically going to be insoluble. This also accounts for, as we were talking about solutions earlier as well, sort of the idea of, solvents and, how come sometimes people always think, for example, water is the only solvent that's ever used. Um, Again, water is really good in a lot of cases because water is polar, which means it pretty much covers, these two big topics. You could do things, you could use water with things that are ionic, you could use water with things that are polar, and that's a pretty broad range. But when we do put water with something that's non-polar, it doesn't work really well with what we were kind of finished up on, like oil and water, for example. Again, they don't mix because they're using two different type of forces. You get this layering that doesn't work. So again, for something that's say non-polar, you would want to use some type of non-polar solvents. Maybe something like hexane and stuff like that, like we talked about in that experiment, where we were using something like we had Cl2, which is non-polar, and use something like hexane, which is non-polar. And by the way, hexane is basically 6 carbons in a row and hydrogens all around, and that's about it. And as we know, carbon hydrogen bond nonpolar, carbon carbon bond nonpolar. This is just a big nonpolar sort of guy. So he's going to use dispersion forces. Cl2, which is nonpolar, going to use dispersion forces. That's sort of nonpolar, nonpolar. These guys work really well together. And again, that's why we saw it. If you remember, we had two layers. This was like the hexane layer, and that was like the water or aqueous layer in that test tube. And remember, this is where the Cl2 would come down, the other guy would come up. We see a change in color in that top layer, but we did have that layering happening first off because these two things don't mix, the hexane and the water, and that's why we were able to get that layering. And again, we always found the non-polar halogen up there because again, those two did mix really well and they would travel into that sort of area. Any questions on the stuff that we talked about sort of last time? Okay, so kind of picking up with what we were talking about there, I think this is about where we left off, if I'm not mistaken. So we talked about the idea of like dissolves like. We also talked about sort of the idea, and we saw a couple of examples that, there are some molecules which, for the most part, you could look at their structure and sort of assess that, there's sort of a non-polar part to their structure and sort of a polar part to their structure. And for example, we saw ethanol earlier as well, and methanol, I think, in a couple of pictures. But ethanol looks something like this. Again, it's an organic compound here. And if you sort of dissect sort of the structure of ethanol as we did last time, there really is this sort of back end of it here where it's really just carbons and hydrogens. And just like, say, we just looked at in hexane, that's going to be nonpolar. But it does contain this bond up in front, which is an OH bond, and that definitely is a polar bond. That's a polar bond over there. Again, the oxygen being more negative, the hydrogen being more partially positive in this particular case. We also saw sort of that effect a while ago there where we talked about soap. Again, soap having that really long carbon hydrogen chain. And as we talked about, I think last time as well, again, pretty long, longer than what I'm drawing actually. Again, it has this sort of non-polar part, which, as we talked about a little bit, is the part that likes dirt, and it has this polar part up in front. Um, and that creates, two type of things. It gives substances such as, say, ethanol, and for example, the ability to be soluble in something like water. Again, it's able to do that because it's a relatively small molecule. It does have that OH bond, which is exactly what you see in water. So they have a way to interact through hydrogen bonding. It also creates different types of regions sometimes that we talk about. And one type of region is sometimes what is referred to as being hydrophilic. And if something is hydrophilic, it means that it is water loving, it likes water. And that's any polar region on a molecule will be hydrophilic because of its attraction to water. And again, in the case of, for example, here, our ethanol, we have our water, which again is also partially negative, or has a negative side and a positive side. we will get that sort of hydrogen bonding occurring and allowing it to be soluble in water. Even something like soap, which again is a relatively big molecule, as we talked about, what it essentially does is it aligns kind of its nonpolar part. I'll just use it as a line here. The nonpolar part around the dirt, but what it leaves on the outside is that polar part. And basically, on the outside of this entire sort of thing, when it traps the dirt, it's all the polar parts, which works really well when we sort of send water in there to wash it. It's hydrophilic on the outside, which means it will mix in really like water and stuff like that. Hydrophobic, on the other hand, is, sort of water hating is basically what it means. And as you can see, again, in certain cases, there are certain molecules, and you see a lot of it in organic molecules, that you can have a side that is sort of nonpolar, and that would be the hydrophobic part that doesn't like water. So that would be obviously this part of it here for ethanol, carbons and hydrogens. For soap, it would also be over here are carbons and hydrogens part. And again, that's why it sort of hides itself along with the dirt on the inside of what creates what is referred to as a micelle with all the polar part on the outside. And that way, it's only the polar part of soap that's interacting with water. Again, here, just a picture of two different things. Here we do see some mixing, and I believe here this is octane and carbon tetrachloride. Octane is basically 8 carbons all bound together with hydrogens, definitely non-polar. Here, as we talked about, I think the other day as well, carbon tetrachloride has a symmetrical geometry, also non-polar, and as you can see, they mix really well here. We take gasoline, which again is all carbons and hydrogens, and mix it with something like water here. We see our distinct layering that's happening. They're really not going to mix well together at all, and we will see that sort of separation that happens, again, because that is polar and that is non-polar type molecule. So guys on the left there, good mixing happening there because they're both using really dispersion forces. Bad mixing here and really little to no mixing happening here because again, gasoline going to be using dispersion forces, water here going to try to be using hydrogen bonding, and again, no long way to keep that interaction basically going. So talk a little bit more about solubility and some of the other stuff that we talked about. When one substance obviously is soluble in another, or mixes or dissolves in another, is said to be soluble. So a lot of times when we think about solubility, we think about, taking, say, something that's a solid and dissolving it in something like water, for example, that's a solvent. Remember that the solute is the smaller part of the solution. The solute is the larger part of the solution. So any type of salt is soluble in water. Again, a salt being ionic, soluble in water, because again, they would be using that ion dipole interaction where basically, as we've seen many times, sort of the ions go into water and then they pretty much get surrounded by the waters. And that's again what allows those guys to really dissolve. When one substance really doesn't dissolve in another, obviously it is said to be insoluble. Oil is insoluble in water. There is usually a limit to the solubility of one thing in another, and as we'll talk about, as we maybe have talked about before, there temperature is a very big role in whether or not something's sort of soluble or not, are the limit to the solubility at a given temperature. So the solubility of things really do change with temperature. So a lot of times if you increase the temperature, you can sort of increase some of the solubility of certain things. Decrease the temperature, you sometimes lower the solubility of things. Now, there are things that are always sort of soluble in one another, and something like a gas is always soluble in one another just by the property of it being a gas. It essentially is in a container, it is essentially just flying around, basically. And that means that it is constantly mixing with one another and constantly, obviously, being soluble in each other. Some liquids are also mutually soluble, so that would go back to what we were just talking about, the idea of like dissolves like, so polar liquids and polar guys and non-polar guys, are also very soluble in one another. Now, when we talk about molecules that are similar in structure, they typically will tend to form solutions. So again, our polar and polar, or nonpolar and nonpolar guys will mix really well together. Now, temperature, as I just mentioned, does play a pretty good role in terms of, sort of the solubility of certain things. So, for example, if you have a solid and you see it's not sort of dissolving, for example, in water or something like that, a lot of times, you can sort of heat it up a little bit or warm it up a little bit. And what that does is increases sort of the solubility of a lot of substances. If you just think about sort of the idea of, you know, dissolving things and breaking bonds. It's sort of an endothermic type process. You need to add heat and energy in there. So when you increase the temperature, you're giving everybody a lot more energy. A lot more energy allows them to sort of break apart, sort of start that dissolving process that occurs. So at higher temperatures, we see a larger solubility of a solid in a liquid. At lower temperatures, we see a larger solubility of a liquid in a gas. So if we just think about for our conversation about gases and how things are flying around and stuff like that. So if we have a gas in a liquid and we have a lower temperature as it's flying around, it's going to be moving a lot slower, which means it's going to be in the liquid part for a lot longer of a time before maybe it would pop out. As opposed to obviously if we had a much higher temperature, the thing may be flying around a lot faster and obviously maybe not be in the liquid part as long. The solubility of gas depends on pressure. The higher the pressure, the larger solubility. So when we think about pressure and volume, those guys are sort of related to each other. As the pressure goes up, right, based on Boyle's law, volume goes down, and vice versa. Pressure goes down, volume goes up. And what that means is as we increase the pressure, we see a much smaller volume. And that would again mean that we have a smaller volume. We got more gas molecules in a smaller area. We would have a lot more mixing of those gas molecules in that smaller area and then be more soluble in one another. And again, here are some of those interactions that we sort of spoke about. This is again when we do dissolve a solid in there. All those pictures that I drew before, but a much prettier picture as most. Again, this is our ionic solid as we talked about at the end of the last chapter, and this very organized, arranged sort of thing. We have all these water molecules in here, and they basically start plucking off these ions. So these are all water molecules. And again, you can see our positive ion in there. The red guy is oxygen. And here around our negative guy, you see the white circles there represent hydrogen surrounding that guy. As we talked about before, that's basically what happens when we dissolve a solid in water is all those water molecules basically get surrounding it. And as we talked about before, you can obviously help this process along by basically stirring it. As you stir it, you're throwing a lot more waters over the surface area of the solid. You're also putting a lot more energy in there as well, allowing that whole process of dissolving basically to occur. When we talk about solutions, there's a couple of different ways that we sometimes will classify solutions depending really on the amount of solute that's sort of dissolved in there. And again, a reminder that the solute is our smaller part of the solution. Our solvent is our larger part. So because there's sort of a limit to how much sort of solid you could get to dissolve in a particular solvent at a temperature, we do get a couple of different types of solutions. What happens if we add sort of too much solute to the solvent? Well, at some point, what will happen is we will hit what is referred to as a saturated solution. And basically, the definition of a saturated solution is a solution that pretty much has hit that maximum limit for how much solid, for example, will dissolve in that solvent. So basically, once you hit that sort of saturation point, is sometimes referred to, once we hit that saturation point, we pretty much have hit the point where that's as much solid as we could get to dissolve in, say, water, for example. If we add any more solid, No more dissolving is going to happen. It's pretty much going to kind of pile up there on the bottom of whatever the beaker or whatever the test tube may be. So saturated solution is that point where you exactly hit the maximum amount that you can get to dissolve. The opposite of that is an unsaturated solution. And an unsaturated solution, we really haven't hit that point yet. So we haven't hit the saturation point, which means that, if we dissolve, say, a little bit of sugar and water, it will dissolve. And we could continue to dissolve sugar and water until we hit basically the saturation point or a saturated solution. And at that point, no more will dissolve. So for example, you could take some sugar packets and like a cup of water, and you get them to dissolve and it will dissolve. If you grab like the Costco size of sugar and you keep dumping it into your glass of water, at some point your water will not be able to handle all of that sugar coming in. You'll just get a pile of sugar on the bottom that you could stir all day and it really won't dissolve. So you at some point hit that saturated solution when really the sugar would stop dissolving. So saturated, really no more could dissolve. You're at the point where you've hit the maximum that it could dissolve. Unsaturated is before that. And that also leaves us with a third type of sort of solution that we sometimes come across, which is what is referred to as a supersaturated solution. And in a supersaturated solution, we basically have a solution where it contains more solute that's present in a saturated solution. So we kind of like hit that saturation point in a saturated solution and we keep going. You could sometimes make a super saturated solution as a common experiment that people used to do years ago. Um, for example, they would make a saturated solution. They would heat it up. And again, they would put a little bit extra sort of solid in there as well and heat it up, and it would get everything to dissolve. Because two things are happening when you do that. When you make that saturated solution, maybe go a little bit past the saturated solution, you start getting some solid piling up. As you heat it, the solubility of that stuff will increase. You'll be able to get that extra solid to basically dissolve, and you'll be left with a solution at that point. Then typically what you do is you kind of cool it down, and two things sort of happen in that sort of situation is you've now made the solution by heating it, allowing it to dissolve more solute than it should. But as you cool it down, two things happen. As it comes back down to sort of room temperature, for example, the solubility of whatever you dissolve starts to decrease and comes down. So the solubility starts to come down, but it's still dissolved in that solution. You also heated it up, so you probably lost a little bit, say, of the water as you were doing that in terms of that. So we end up with, at the end, as you do that, is this super saturated solution. Where right now it's a solution, it's kind of an unstable solution. It's so unstable because you basically have now created a situation where you have all this solid dissolved in the solution, but it's really too much for the solvent because you were able to get all that solid to dissolve by increasing the temperature. But then as it cools back down, it realizes I got like way too much solid dissolved in there. It is so unstable that in like an experiment like this, for example, that I'm describing, you literally, if you're not careful enough, if you just kind of tap the side by accident on something, it will cause really everything to kind of come out of solution. But usually in an experiment like this, what they'll do is they'll take like one small little crystal like that, for example, of whatever was dissolved in the solution. And at this point, it's still a solution. They basically will just drop that guy right in. And as soon as that one little small, barely could see sort of crystal of whatever was dissolved in there hits the solution realizes, whoa, I got way too much solid in here. And what ends up happening is you actually start to see all the solid will come out of solution. And it will go really from a solution to basically a rock hard solid. And you could actually see all the solid basically coming out of solution. So sometimes when we create sort of a super saturated solution, it's a sort of unstable solution in that sense, the solid wants to sort of come out of solution. And again, we do see an increase in sort of the solubility. And we'll just look at it. This is for ammonium chloride, for example, in 100 grams of water. And what we see here is we go at sort of a lower temperature, the amount of ammonium chloride that you could dissolve, for example, at say 10 degrees Celsius is right around here. So 30-ish grams per 100. If we really increase the temperature, say to 100 degrees Celsius, up here we can see we're pushing about almost 80 grams per 100 grams of water. So we see this increase in solubility of some type of solid like ammonium chloride by increasing the temperature. Here's a picture of what I was just talking about. So basically what we have here is a supersaturated solution. This is like acetic, this is sodium acetate, I believe. And you can barely see it, but like right about here, they just put like one little crystal of this sodium acetate that was dissolved in there. And you can see as it goes in, it starts to hit here, and you can start to see the crystals. These are actually the crystals starting to come out of solution by just simply adding that one little drop. You can see it starts to build, it starts to build. It's kind of a cool little experiment. And eventually this entire thing, all the solid comes out and becomes sort of rock hard at that point, and you now have a solid. And I've seen people do this experiment, for example, and like I said before, it's sometimes so unstable that if you just sort of knock it, putting like the beaker down or the flask down too hard, it will actually cause this whole process to occur without you even having to add anything. And that's again because we create this sort of solution that's relatively unstable because we have now dissolved way too much solute in that solvent. Question on saturated, unsaturated, supersaturated solutions. All right, so in terms of gases and solubility, pressure obviously plays an important role in terms of the solubility of a gas. External pressure has an effect on that solubility. A relationship between sort of the pressure of a gas in a liquid sort of situation and the concentration is Henry's law. Henry's law says that the solubility of a gas is proportional to the pressure of the gas over the solution. And a couple of things here. This is really concentration or molarity, or sometimes it's referred to as the solubility or molar solubility a lot of times. But it's really molarity, which is really just moles per liter. This is obviously the pressure here, probably in atmospheres. And it does sort of depend on this guy here. This is Henry's laws constant. So this is basically a constant. And it is specific for a different substance. So it's sort of substance specific. This is a value that you could typically look up on a table. And you can use this to figure out the pressure needed to keep a certain concentration of a gas in a liquid. You could use it to figure out really what the concentration of the gas is at a particular sort of pressure. So this is again a table of Henry's laws constants, which obviously would be provided for you if you should need it. You should always, again, on any type of table value, always look at the units to make sure they do agree with what you think it would agree with. And really, Henry's law describes sort of what we see when we talk about sort of a soda can, for example, with soda, right, in a sort of a canned soda situation. We definitely have a can that's under pretty high pressure. And under high pressure, as we talked about, we're going to get a larger solubility of gas molecules in the liquid part. So a lot of the gas will be in the liquid part under that high pressure, as we can kind of see here. Basically, CO2, right, is the gas we're talking about here in like a soda can. And under that high pressure, we're going to get all those gas molecules basically remaining in the sort of soda part, if you will, the water part of the soda. When we release that pressure, which happens obviously here when we pop the top, we're doing two things. Obviously, we're releasing the pressure, which is going to allow the CO2 molecules that were dissolved in the solution here basically to be released. So they're going to find their way out of the solution. In addition, we also gave it an escape route there out the top of it, which is all that fizzing we see coming out of the top. And basically, by releasing the pressure and also giving it an escape route, we're doing two things. We obviously are making the gas less soluble, the CO2 less soluble in our soda. And that is why, right, that when we have an open can of soda, for example, and you leave it out for a while and you go back to it, it tastes flat. And it tastes flat because all your CO2 molecules basically just exited the building there, and you're left with basically syrup or water here or whatever's in your soda, I suppose. So that's sort of what Henry's law sort of describes. We could calculate concentrations and pressures associated with this. So why don't you try this? What is the pressure of CO2 that's required to keep the concentration of CO2 at 0.12 in a 25 degrees Celsius situation here? The Henry's law constant that you can find for CO2 is 3.4 times 10 to the minus 2. So take a second and see what you come up with. Okay, so let's take a look here. So again, we could use really Henry's law. And as I was mentioning before, this is sort of another version of Henry's law, which is this one right here. And you may be wondering, sort of what does the S stand for? The S stands for here solubility. And as I mentioned before, a lot of times with Henry's law, they were used talk about molar solubility. So sometimes people refer to it as concentration, like we saw in the previous formula, and sometimes people will refer to it as S or solubility or molar solubility. They're really all sort of talking about kind of the same things. They're talking about really the moles per liter, how much of the solute you can dissolve in that particular solution. Which is basically the solubility of it as well. So it's basically the same formula, but sometimes people will use some different sort of symbols to represent the same things. So here, if we just rearrange this, we do have obviously the concentration given to us, and that's what this would be. This number here technically would be the molar solubility. Our S, our C in the previous sort of formula. So we would be rearranging it and solving for the pressure here. And again, our Henry's law constant would be looked up, and it would be looked up for CO2. So that's an important fact. Remember that as we looked at this table here, when we look at something like CO2, it has a different Henry's law constant, for example, than if we were dealing with a different gas like oxygen. So again, it is specific for the actual substance that we're looking at. And if we put it in, the molarities cancel, the atmospheres come to the top when we do it, and 3.5 atmospheres would be the pressure required to do that. Remember that kind of standard pressure is 1 atmosphere, so this is about 3 times or so the standard pressure that we see, say, in a can of soda to keep our CO2 basically dissolved in there. Any questions on it? Right there. All right, so since we're talking about solutions and stuff, we're going to kind of review a couple of sort of units that we talked about before in terms of concentration units. And again, I believe this should be most of this review here. But again, there's several percent units that we talked about when we talked about solutions. This is, again, percent mass to mass. And remember, when we do percent mass to mass, the bottom part here, which is the mass of the solution, is the important part. You want to make sure that you actually get both parts of the solution, both the solute and the solvent together. There is also percent volume to volume that we talked about, which was the volume of solute. If I could write volume of solute divided by the volume of solution times 100%. And remember, there was percent mass to volume, which is the mass of the solute divided by the volume of the solution times 100%. So these were several percent sort of concentrations that we used. We also talked about sort of how to use those as conversion factors as well. Again, you could assume that you have 100 of something and basically put those guys in there as conversion factors. So if we had, again, a 4% by mass sodium chloride solution, as we talked about, that basically means you have 4 grams of sodium chloride and 100 grams of solution. So we talked about sort of using those guys as sort of conversion factors. So when we do a process like this, a reminder that when we read a problem, we have the 2.5 grams of calcium chloride dissolved in basically 50 grams of water. This right here is our smaller part, which is our solute. This obviously is our larger part, which is our solvent. And when we're calculating the percent mass to mass, we want to make sure that we, get both of those guys together. So the percent mass to mass, which I think we did this example earlier, again, the solute, which would be 2.5 grams, we want to make sure that we do add those together to get the solution part of it and times it by 100. And that would again give us our 4.76% by mass here, sodium chloride. A reminder that, again, sometimes people will just use the solvent part here and not the actual solutions. So it's really important to get both of those because, again, very common that those guys are given to you sort of separate in this calculation. Any questions on that calculation there? And again, here we have 37.2% by mass hydrochloric acid. Again, that is the mass percent is 37.2% HCl. We want to know what is the mass of the HCl here. Again, the HCl is going to be the solute. Basically, the name of the solution is always the solute. And that means that the mass of the solution is going to be 35.5 grams. So we could do this 2 ways, as we talked about. You could plug and chug into our percent mass to mass sort of formula. You do your mass of the solute, mass of the solution times 100%. Again, you could do it sort of as a conversion factor as well. And basically what that means is you have 37.2 grams of HCl and 100 grams of solution. Or again, you could flip it around, and 100 grams of solution, you have 37.2 grams of HCl. So if we sort of use a conversion factor way, again, 35.5 grams of our solution, we would use the conversion factor on the left there, which is our 37.2 grams of HCl, 100 grams of solution. The grams of solution will cancel each other out, and we will be left with 35.5, 37.2, and 100. 13.2 grams of HCl would be dissolved in there. Question on that particular one there. So again, that's just sort of a review of some percent concentrations, which I believe we kind of went over earlier as well. Another sort of concentration unit that we, I believe, talked about as well is molality. Again, a reminder that molality is different than molarity. So molality is lowercase m, and it is equal to, as we see on the bottom there, moles of solute over kilograms of solvent. Again, not to be confused with capital molarity there, or capital M, which is moles of solute over liters of solution, and that's molarity. So they are, again, different sort of units. The thing that ties them together, as I think I might have alluded to earlier in an earlier chapter when we sort of talked about these guys a little bit, is it is density. Basically, is sort of the thing that ties those two together. If you know sort of the density, you could kind of go from molarity to molality and backwards as well. And again, to do molality here in problems such as this, we want to calculate the molality of a solution prepared by dissolving 61.7 grams of C3H7OH. We would need the, again, moles of the solute over kilograms of the solvent. The moles of the solute in this case would be what we're dissolving in there. And if we did our molar mass of that guy there, we got 3 times 12.01 plus 8 times 1.008 plus our 116 there, which is 6009. So we could right off the bat just take our grams and convert these guys again into moles. And if we do that there, we get 1.03 moles. Water is our solvent, but it is in milliliters, and we do have the density. So density is mass divided by volume, which means that mass would be volume times density, which means in this case 175 milliliters times our 1 gram per milliliter means we have 175 grams of water, which is our solvent. We can convert that 175 grams into kilograms by dividing by 1,000, or moving the decimal point. 0.175 kilograms. That means we can now get our molality by taking 1.03 moles divided by 0.175 kilograms, and we end up with a 5.87. And again, much like molarity, the units don't cancel, so it is moles per kilogram. Or you could write it just like molarity, but with a small m at the end of it to indicate molality. Any questions on molality? So I think we saw that earlier when we were talking about molarity. And again, it's a good reminder because later on this chapter here, we will definitely use molality again in a lot of aspects. We will use it to calculate a lot of things involving colligative properties. So again, molality, we will now see sort of in several calculations in this chapter. In addition, another thing that we talked about previously that we will see kind of in this chapter again in terms of calculations is our mole fraction. Remember that our mole fraction is usually abbreviated with an X, and basically if you're looking for the moles of A divided by the total moles that are present, and remember this is kind of like a percentage without the multiplying by 100, but basically gives us sort of the percentage of each of those moles that are present. So again, if we had a mixture of a couple different things like mole A and mole B, and we wanted the mole fraction of A, we again would take the moles of A divided by the total moles that are present, and that would give us our mole fraction. As we can see here in this example that I think we did earlier, calculate the mole fraction of methyl alcohol in a solution of methyl alcohol with ethanol. So we would look for our total moles here to do this and divide it out. And what we see is we end up with 0.261. This being, again, the moles what we were interested in, which in this case was the methanol. This being our total moles. Although it's really not considered a percentage, it basically is telling us it's 26% made up of methanol, which means it's about 74% or so there. a little less than that, made up of ethanol. Again, you can do the same thing for ethanol. It would just be our 0.929 moles divided by our 1.257 moles, which hopefully is the total there for our C2H5OH. Roughly gives us 0.739, which is about 74% ethanol, about 26% methanol, even though technically speaking, obviously it is not a percentage. So those two things that were just sort of reviewed there are really important for what we're going to talk about in the second half of this chapter, which is colligative properties. We definitely will use molarity again in a lot of calculations, and we will use the mole fraction also in several types of calculations that we will see. And since we're reviewing, obviously, molarity is one that you should obviously know, hopefully by now. And again, molarity, which is our big M, basically means moles per liter, moles of solute per liter solution. And remember that we can use this to rearrange in several ways. Liters would be our moles divided by our molarity. Moles would be our liters times our molarity. And a reminder, as we've talked about before, that, if you are using molarity sort of by itself and you want something like moles, you definitely do need to convert the volume into liters. As we talked about, if you actually multiply milliliters by molarity, you get millimoles, as we talked about, and not moles. So remember that. So you'll be off by a factor of 1,000 if you don't sort of do the multiplication correctly. If you're doing something like the dilution equation that we've used before, this one, because there's two molarities, two volumes, this one you do not have to sort of convert into milliliters as long as both volumes are in milliliters, because if we take molarity times milliliters here, that gives us millimoles, and then if we divide by milliliters here, the millis cancel out, brings us back to moles per liter, which is molarity. So a reminder, as we talked about, if you use the dilution equation, you don't necessarily have to convert it to liters. You can, but you absolutely should definitely convert it to liters if you're using just kind of volume and molarity by itself. Any questions on that there? All right, so we will lay it up there.